This is section 2.2, part 3. So continuing where we left off, we were talking about rates of change. In general, the position function s of t for an object moving along a straight line, its velocity will be the limit as delta t approaches 0 of the average velocity. So if we, well, like we did in that last example, we went from 1 to, let's see where that was at, 1 to 2, then from time 1 to 1.5, then from time 1 to 1.1. As we squeeze down on the point Q, going from 2 to 1.5 to 1.1, where point P is staying 1, what we're doing there is we're making Q approach P, and as we saw with secant lines, as Q approaches P, we get the instantaneous, we get the slope of the tangent line, which is like here finding the instantaneous rate of change. If we do the limit as delta t approaches 0 of the position at the end, which would be maybe expressed as t plus delta t, minus the position at the beginning, s of t, all over delta t. And that, if you look at it, is the definition of the derivative of s prime. Is the derivative of s, called s prime of t. So this is the velocity function. And so one of the first things here that I want you to make sure that you know is that velocity is the derivative of position. Velocity function is the derivative of the position function. That's really important that you understand that, because that will come up in a lot of applications. In other words, the velocity function is the derivative of the position function. Velocity, of course, as you know, can be negative, meaning you're going left or down, typically. It could be 0 if you're stopped, or it could be positive, that is, you're moving right or up. The speed of an object, however, is actually the absolute value of its velocity. Speed can't be negative. If I'm saying I'm going from Dallas to Fort Worth at 50 miles an hour, when I go from Fort Worth to Dallas, I won't say negative 50 miles per hour. I'll still drive a positive. So speed is always positive. And mathematically speaking, the value of the speed is the absolute value of the velocity. So if we're going 20 miles an hour to the left, the velocity will be negative 20, but the speed will be 20 miles per hour. So that's how those two are related to each other. All right, so if you have a free-falling object, assuming there's no air resistance, and we do this in math and science classes all the time, is make assumptions about how everything's perfect. Well, let's just pretend like there's no air resistance. The position of a free-falling object under the influence of gravity can be represented using this equation. In general, if something's falling, it will follow this position function, negative 1/2 times g, which is a constant, which we'll refer to as the gravity, the amount or the size of gravity. Of course, on the Earth, that has a specific value. On the Moon, it's different. On Mars, it would be something else altogether. But g stands for the acceleration due to gravity. So that's a constant, times t squared, plus the initial velocity of the object. It could be dropped, which means it would start out at velocity 0, or it could have been thrown down. And so when it leaves the hand, it might have if it's going down, a negative velocity, or if you throw it up, it would have a positive velocity, times t, initial velocity times t, plus the initial position S sub naught. So the S sub naught is the initial height of the object, V sub naught is the initial velocity of the object, G is the acceleration due to gravity, T is the amount of elapsed time, and S is the position. Now, on Earth, the value of that constant that we're going to use, although at different places on Earth it might be different, like high on a mountain or way down low, that can be changed. But we're going to say that that is, on Earth, approximately, change that. On Earth, G will be approximately 32 feet per second per second. Okay, or feet per second squared, if you're using feet and seconds as your units of measure. Or if you're using meters and seconds, G will be 9.8 meters per second, also known as meters per second squared. Okay, so those are the two constants that you'll need to know with this formula. And if the problem is dealing in feet, G will be 32. If the problem deals with meters, then G will be 9.8. Okay. So, at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. So here's the board. So this is the board. And here's the water. And this distance is 32 feet. Okay. And so you have a guy or a woman who is up here ready to jump off the diving board and land in the pool. Well, since that board is flexible, it actually flexes up and down, especially more at the end of it. When the diver leaves the board, they're going to first go up some and then come back down. So that's the path that they'll take. And as long as they're not impeded by some other medium, like instead of air you go into water, you'll no longer follow the same S function curve, because there is air, well, it's not air, it's water resistance at that point that's occurring. So keep that in mind, that this curve only is useful until they hit the water, and then it's no good after that. You can't use this. All right. The initial velocity is 16 feet per second. So this diver is going upward at a rate of 16 feet per second. Because it's positive, that's how I knew it was upward. We have two questions. When does the diver hit the water? Hit, you might want to say enter if that hit makes you a little bit uncomfortable. I was really afraid of diving into water from high up, so I thought I'd get hurt. So hit sounds terrible to me. So anyway, and then the second question is, what is the diver's velocity? Velocity at impact. Again, that sounds horrible to me. Sounds hurt, like it would hurt a lot. All right. Well, anyway, enough of my phobias. I actually overcame that, was able to dive, but when I was a little bitty guy, I didn't want to do it. I think partly because I saw someone try to do a flip of some sort, and they hit their head on the diving board, and it was gross. It was bloody and scary and all that stuff. Anyway, so we're going to start this problem with what we know is true about this situation, the diver's position, S, which is represented by this curve right here, is -1/2 times g. And since we're given the distance from the board down to the water being 32 feet, that means g involves feet per second squared, so that's 32. That's our g value, times the variable t squared, plus the initial velocity is 16, multiplied by the variable t, plus the initial position, which is 32 feet above the water. And so S of t would simplify to be -16 t squared plus 16t plus 32. All right. Now, when does the diver hit the water? Well, what you need to do is translate that question into mathematics, mathematical statements. And when the person hits the water, if their position S is measuring distance above the water, then when the person hits the water, what is his position? Well, yeah, his position is 0. So what we're going to do to answer the first question is we're going to let S of t equal 0 and solve for t, which will answer the question when. When is a value of t? So that's what we need to solve for. So that means -16 t squared plus 16t plus 32 will be 0. I notice that I have a common factor, and I'm going to factor out -16, which will leave t squared minus t minus 2 equal to 0. Then I hope that factors. It does. Factors to be t minus 2 times t plus 1, which means that this happens at t equals 2 or t equals -1. One of those doesn't make much sense to me at first glance, but if we considered S of t as a complete parabola that includes all points that you could get from that parabola, then the continuation of that parabola would take you back here, which is not what happened to the diver. The diver didn't come up through the water, up through the board and do that. But the model shows that. And so this time, as if the person did get accelerated from the water up over the board and back down, that would happen 1 second before the person is at the board. And this point would happen at time 2. And of course, that's the situation we're dealing with. So we'll keep this answer, and the other one is considered extraneous. It is a solution to the model, to the quadratic equation, but it's extraneous to our problem situation, and so we'll just throw it out. Okay, so our answer will be, for the first question, the diver hits the water um, 2 seconds after leaving the board. Okay. Okay, on to question number 2. So I guess I should number these up here. They weren't numbered in the notes, but I'm going to number them just for convenience. So what is the diver's velocity at impact? Well, since we have the position function right here, the velocity, which is what we're asked about, is always going to be the derivative of position. And since we have those differentiation rules at our disposal, we can say that that will be the constant -16 times the old power times t to the reduced by 1 power. 2 minus 1 is 1. I'm not going to write the power of 1. Plus 16 times 1, or just 16, plus 0. So the velocity function, the derivative of position function, I should say, is equal to -32t plus 16. You might notice in problems that involve time, I try to make my t sort of a cursive t, has a little tail, and my plus signs I try to draw straight. You might want to adopt that so that your t's and plus signs look different from each other. I've had to read students' work where I couldn't tell a t from a plus sign at all. It made it really difficult to grade their work. Okay, so number 2. What is the diver's velocity at impact? Well, we know that they hit the water at 2 seconds, so the velocity at that point in time is going to be the velocity at time 2. And so by substitution, that's -32 times 2 plus 16, which is -48. And the units are feet per second. It's negative, of course, because at that point the diver is moving in a downward direction. And the speed is 48 feet per second. They didn't ask us for speed, they asked us for velocity. So I do need the negative on that answer to be correct. All right, so that ends this lesson. I will see you in class.